One of the benefits of creating a comprehensive domain model is that it feeds directly into the design of a relational database. A correct domain model always provides an accurate, well-designed relational database. Let's learn how to translate the information on a domain model into a relational database. We start with a few basic definitions. A relational database is a database structure based on the relational model. In essence, a relation is like a table and consists of rows and columns. Each row is a record and each column is an attribute of the relation. A relation or table is similar to a spreadsheet with rows and columns. However, a relational database is much more powerful than a spreadsheet. A relational database has many relations or tables. Each one is considered a separate file. Each one has many records where each record is similar to a row in a spreadsheet. The columns of the tables are attributes of the relation and correspond directly to the attributes of a class. An attribute value is the same concept that you learned previously. Each row will have a distinct value for each of the attributes. Here is an example of a relational database table. Along the top row are the names of the columns or the attributes. Going down from top to bottom, all the rows are listed. Each column shows the individual values for each row. Each field, the same thing as a cell in a spreadsheet, contains the value of a particular attribute for a particular row. Because keys are such an important part of a relational database, let's define a few terms about keys. A key is an attribute, or in other words, a column, or perhaps two or three attributes together which uniquely define a row. In other words, every row has a unique value for its key. Because the key value is unique for each row, we can use the key to find individual rows. It is possible for there to be more than one column that has unique values. For example, as a student, you probably have a student ID. In the university, you also have a social security number. Both of these are unique to you. We say that both the student ID and the social security number are candidate keys. In other words, either one can work as a key. However, as developers, we decide and assign only one of them to be the primary key. In the university case, we might assign a student ID to be the primary key for the student table. A foreign key is the primary key of one table that is placed in another table. Suppose there is a table of courses and another table of course sections for a particular semester. And suppose that there was also a table of teachers. The teacher table would have teacher ID as the key and the other information like name, office, etc. If we put the teacher ID as a foreign key in the course table, then we can tell which teacher is teaching a particular section of a course for which semester. Here is a domain model that will help us understand foreign keys. In this model, there are product items. For each product item, there are several inventory items. The inventory items for a single product are different for each size and color. There will be a quantity on hand for each inventory item. We will need to know for each inventory item which product item it represents. Here is how this example is given with foreign keys. There are two tables, the product item table and the inventory item table. The inventory item table has a foreign key of the product ID. Each row of the inventory item table points back to a row in the product item table. Product ID in the inventory item table is a foreign key. It is the primary key in the product item table. We learned something from this example. Notice that each class became a table. Also notice that we captured association information as foreign keys in one of the tables. This is the process that is used to convert an entire domain model into a relational database. Let's review this procedure. These are the major steps. First, create a table for each class in the domain model. Second, choose a primary key for each table. You might have to invent one. Third, add foreign keys as we just learned for the one-to-many associations. Fourth, create new tables for the many-to-many associations. These are the association classes. And fifth, create appropriate tables for generalization, specialization, relationship. Let's do each one. Here's a portion of the RMO model. In this diagram, there are 12 primary classes. We won't look at each one of these right now. Let's just proceed. Step number 1, create a table for each class. In this diagram, we have created 12 tables. We named each table with the same name as the class. We listed all of the attributes from the class table. The names of the attributes are capitalized in the database. This convention will change depending on the DBMS that is used. But for now, let's just remember that for database design, we capitalize the column names. You may want to stop the video for a minute and look at this detail. Step number 2, we choose a key for each table. Invent a key field if necessary. In this diagram, we have given each table a key. In most cases, we invented the key and called it with the table name plus the letters ID. For the customer table, however, we use the customer account number. The key for each table is written in bold. Step 3. For one-to-many relationships, add the primary key of the class with a multiplicity constraint of 1 to the class with a multiplicity constraint of many as a foreign key. In this example, there are 3 associations we will look at. As we saw in the previous slide, the product item has a one-to-many relationship with the inventory item. Also, the cart item has 2 one-to-many associations, one from inventory item and one from online cart. Let's predict what is needed. First, the inventory item will have a foreign key of product item, ID. Second, cart item will have 2 foreign keys, one from inventory item and one from online cart. Let's see. Ah yes, here are the results. Inventory item has a primary key of inventory item ID in bold. It also has a foreign key, as shown in italics, of product item ID, just as we predicted. The foreign key indicates which product item the inventory item belongs to. Cart item has a primary key of cart item ID in bold, and 2 foreign keys, inventory item ID and online cart ID, both in italics. The foreign keys indicate which inventory item is in the cart and which cart the cart item belongs to. One other point. We did not discuss one-to-one associations. One-to-one associations are fairly rare, because all the attributes of a one-to-one can just be placed into a single class. However, for rare occasions, when you find one, just put the primary key of either class as a foreign key in the other class. Either direction will work. Other considerations will indicate which direction is best. Step number 4. Create new tables to represent the many-to-many associations. Let's look at these 2 many-to-many associations. How do we capture that information? We cannot put the primary key from one class into the other because we would need multiple values. The solution is to create a new table with both primary keys as foreign keys, just as we did with the association classes. In this diagram, we have 2 examples of many-to-many associations. For one of the associations, we already have created an association class called promo offering. For the other, however, we do not have an association class. The procedure is the same for both, however. Create a new table as an association table. The primary key for the new table is the concatenation of the primary keys for the connected classes. Let's see. Let's look at the promo offering first, since we already had a class for this one. In promo offering, notice that the 2 endpoint keys, promotion ID and product item ID, are in bold and are italicized. The bold indicates that they together serve as the key for the promo offering table. The italics indicates that they are both foreign keys from 2 other tables. The other attributes in the table are included. The table for the association between accessory package and product item has been named accessory package contents to somewhat indicate its meaning. The only fields in this table are the 2 other keys as foreign keys, accessory package ID and product item ID. Together they also make up the primary key of this table. Step number 5. Represent classification hierarchies. In this figure, there are 2 generalization-specialization hierarchies. Remember that the subclass inherits all of the attributes and the associations of the superclass. Also, any object in a subclass is also in the superclass. For example, an in-store sale is a sale, so an in-store sale object is also a sale object. Given that the objects are in both classes, if we create a table for each class, then we would assume that there will be a row in each table, in the superclass table and the subclass table. What is the key of the subclass table? Well, it will be the same as the key for the superclass table because it's the same object. There are 2 ways we can represent this hierarchy in the database. One simple way is simply to move all of the attributes, all the subclasses, into the superclass and have one expanded table. Of course, this would mean that for some rows there will be null values for those fields that don't apply. So there will be some wasted space. But this is a workable and a simple solution. It is simple because all the data is in one table. The other approach is to make tables for each class, for the superclass with its attributes and for the subclasses with their attributes. Again, all the tables in the hierarchy would have the same key. Let's look at these 2 solutions. This is the combined solution. In this example, we have combined the subclasses with the superclasses. Notice that the online cart includes the attribute elapsed time from the active online cart and the attribute hold for days from the on reserve cart. The same solution holds for the sale table. The attributes from all of the subclasses are included in the sale table. In this example, we have separated all the tables. Each table holds only its primary key and its own attributes. So the active cart has a primary key of online cart ID and an attribute of elapsed time. The on reserve cart has the same primary key and the attribute of hold for days. The decision whether to combine or to separate is based on other issues, including technical issues and how the data will be accessed. One last point. Remember that we indicated that the online cart and the sale are both abstract classes with no objects. Because they are purely abstract objects, we could also eliminate the abstract table and push all the attributes down to the tables for the subclasses. As you can see, there's quite a bit of flexibility in how we handle classification hierarchies. In summary, we've gone through 5 steps to convert a domain model diagram to a relational database. As mentioned earlier, if the domain model is done correctly, the result will always be a correct relational database.